All right. Hopefully, you are feeling refreshed and ready to begin a whole new chapter, chapter 3. We are starting with systems of equations. So, here, 3.1, we're going to look at one method of solving systems of equations. We're going to be looking at the method of graphing. And then in 3.2, we're going to look at more algebraic methods, the method of substitution and elimination. Okay. And then in 3.3, we will look at how to solve systems with 3 variables. Okay, so let's go ahead and start. Take notes, have your phone ready in case you have any questions. Use the CC button down below if you need subtitles. Solving systems by graphing. Okay, so let's just kind of recall graphs in general and what they represent, okay, because we started graphing by analyzing the equation and pulling out important information and then just graphing it that way. But if you remember, we originally started graphing by making a table of values, okay, and maybe we got a line, okay, and let's just remember that the graph here actually represents all the xy solutions, okay, so of whatever equation that you just graphed, okay, so whether it's a line or a parabola or an absolute value, remember that the graph still represents all the xy solutions, all the x and y's that satisfy the equation, okay, so the graph represents all the xy solutions of a given equation. Like maybe you have a linear equation, negative x plus y equals 2. Okay? All right, so now what we're going to be doing is we want to find the x and y solutions that satisfy not just one equation, but multiple equations simultaneously. So great, all of those, like here, all of these x and y points satisfy this equation. But what if we have another equation? And we want to know, okay, well, which x and y works not just for this equation, but also works for another equation. Okay, so that's what we're going to be doing here. We want solutions that satisfy multiple equations at the same time. Okay, so if I have this line, okay, then this line here represents solutions to one equation, right? Represents solutions to equation 1. So that's great. But again, we are looking at more than one equation, and we want to know the x and y solution that satisfies both of them. So maybe this line represents the solutions to our first equation, and then maybe this line represents the solutions to our second equation. Okay, And so what happens is we're trying to find the x and y that satisfies both of them. So this satisfies all of these x and y points, right? Satisfy equation 2. All of these satisfy equation 1, but only this xy coordinate right here where they intersect is the only solution that satisfies both. It's the only xy that they share. Okay, it's the only xy that is a solution to both equations. Okay, so right over here, this point, okay, right there, okay, that point this point of intersection is a common solution to both equations. And that's what we want. So we're not just solving one equation, but we are solving two. Hold on a second. A squirrel just came in. Jarrett? Jarrett? Okay, never mind. So we kind of have a pet squirrel. It's a neighborhood squirrel, and we named it Diego. And he's gotten kind of comfortable, and he just kind of comes in sometimes. And he's in here right now. Hold on. Okay, I don't have a pause button, but the squirrel is on our kitchen counter. Hold on. Diego. Diego. No. I'll give you one walnut. I'll give you one walnut. Okay, sorry about that. All right, so the point of intersection is the one that we want. So when we do this graphing method, we will be graphing both equations, and we will estimate the point where they are intersecting. Okay. All right, so here are some possible scenarios. Okay, so we have the case where, okay, great. They intersect and one solution exists. It's that point that they both share. Okay, so this is the one solution case. And we call this consistent. Okay, another scenario is if we have parallel lines. Okay, well, if these are parallel lines, they never intersect and they never have a common solution. They never share a point. So here, they would have no solution. So no solution. And we would say that this is inconsistent. Okay. We also say that this is independent. In case your homework asks you for these categories. Okay, and then we have this third scenario where maybe you have this line and your second line falls right on top of it. Okay, in which case here they are actually intersecting at every single point. So here they have infinitely many solutions. Okay, and here we say this one is also consistent. And we say this one is dependent. Okay. All right, so let's take a look at an example. Let's go ahead and solve by graphing. So solve by graphing. And we looked at 2 ways to graph lines. It doesn't matter to me which method you use. I think they're both, depending on how the equation is written, they're both pretty easy to use. Okay, so let's suppose that we have these 2 linear equations. X plus 2y equals 4. That one's in standard form. 2x minus y equals 3. Also in standard form. Some of you guys might want to rewrite them in slope-intercept form and use the intercept and then do your rise over run. To me, whenever it's in standard form, it's just as easy to do in my head the intercepts. But I will not do it in my head. I will show you in case some of you guys are not sure how to come up with the graphs. Okay, so I'm going to choose 0 for x. And like I said, normally I just do it in my head. Plug 0 in for x, and I get 2. Okay, so I get 2 for y. Okay, and then I like to choose 0 for y. So I'll plug that into, again, the first equation, plug in 0 here, and I get x equals 4. Okay. All right, so I would go ahead and graph this first equation. So 0, 2, 1, 2. Okay, so 0, 2, right over here. And 4, 0, 1, 2, 3, 4, 0, right over here. So I have this line. Okay, equation 2, I will do it the same way. Again, I would not normally do a table of values. I would just do it in my head. X is 0, y is negative 3. Okay. X is 0, y is negative 3, y is 0, x is 3/2, which is the same as 1.5. Okay, so 0, negative 3 is down here. 1.5, 0 is right there. And so when I graph this line, I get that. And again, I'm looking for the point of intersection here, and it looks like it's 2, 1. Okay. The thing about graphing method is that if you graph a sloppy graph, then maybe your answer is right. Maybe it's a little bit off. Okay. So, and also, who's to say maybe this is 1.99, right? Who knows? Okay. All right. But this is a method nonetheless. And we can always check our solution by taking 2, 1 and plugging it in here to the first equation to see if it satisfies the equation. If I plug in 2 here and I plug in 1 there, 2 plus 2 equals 4, yes. And then you have to check to see if it satisfies also this equation. So let's take 2, 1, plug it in here and here. 2 times 2 is 4 minus 1, 3, yes. So 2, 1. This is actually a pretty decent graph considering I was not trying to be careful. So 2, 1 satisfies this. Okay. All right. So let's go ahead and have you guys try this one. And let's see if we get the same answer or pretty close. Again, depending on how neatly you graph, we may or may not get the same answer. Okay, so go ahead and solve by graphing. Two x plus 5y equals -1. X minus y equals -4. Okay, so go ahead and hit the pause button, and I will solve this as well. Okay, so if I am going to graph this, okay, so I am going to make a table of values for the first equation. When x is 0, y is -1/5. When y is 0, x is -1/2. Okay, so 0, -1/5, -1/2, 0. So right here. Okay, equation number 2. When x is 0, y is +4. When y is 0, x is -4. So 0, 4, 1, 2, 3, 4, right here. -4, 0. 1, 2, 3, 4. Uh-huh. So here, this is a graph that was pretty sloppy. Okay, so here, and I wanted to use this one to emphasize the fact that that we would need better methods to graph this. I think one of these is wrong. 0, hold on a second. 2x plus 5y equals -1. X minus y equals -4. When x is 0, -1/5. When y is 0, -1/2. When x is 0, +4. When y is 0, -4. 0, 4. Ooh, I graphed the wrong point. 0, 4. Okay. 0, 4 is up here. 1, 2, 3, 4. And so we have this line. Okay, so that makes more sense. And right here, this point of intersection looks like, again, this is kind of sloppy. 1, 2, 2. All right, my graph looks like the solution is that -2, 2. If you did a nice, neat graph, then you would have gotten the correct answer, which is actually -3, 1. Okay, that's the actual answer, which is very close to this. Okay, I'm only off by 1 on both of these values. Okay, so again, depending on how neat your graph is, you may or may not come up with the exact solution. You might be very close. Now, if you ended up with a point that's not even close to the actual, because look at, here's the actual solution. Let's go ahead and plot it. It's down, it's over here. -3, 1, 2, 3, 1. Okay, so there's the actual one, right? Okay, so if you ended up with a point that's way down here, you're not even close. You're not within like a 1 unit radius circle away from your answer. You're like way out here in a whole different quadrant. Then you're really off, and there's probably some mistake in your answer. Okay, but I wanted to use this one to emphasize that graphing method may not be the best method to use to solve systems of equations, but it helps us to see if our solutions from using other methods makes sense. Okay, so here we use graphing method. So in the next section, we're going to be looking at more precise methods of finding the solutions. We're going to be looking at algebraic methods. Okay. All right. So make sure you do your graphs nice and neat so that you get as close to the right answer as possible. Try to use graph paper if you have it. If not, not a big deal. But you'll be doing on WebAssign, and they do have the graph for you. All right. Again, if you have any questions, make sure you email me or send me text messages. I will see you next time.